Okay, now, here is what I am going to look at to begin is a detonation. And I start with what is called an over-driven detonation. What is an over-driven detonation? To figure out what is an over-driven detonation, you think about the same experiment I developed for you for the shock. That is, you have where is it? Where is, oh, you have a fresh mixture here, you have a shock, and across the fresh mixture, it's at temperature so low that there is no reaction, okay? I will be back to that later on to be very clear about that, that the initial mixture is frozen. There is no reaction. Then a shock propagates, and then it increases the temperature. Okay? And because you increase the temperature, the reaction starts. The reaction starts and develops behind. And now let me just fix the notation. So I will call now the flow velocity going out from this detonation structure, UB, relative to the structure. You have the fresh mixture enter with a propagation velocity, supersonic propagation velocity into the structure here, and it goes out with UB. Now, the relation you have between this UB and V and the velocity of the piston is simply the change of referential frame is T minus VB. It turns out that this UB is, first of all, D is all the time larger than unity, larger than the sound speed, Mach number larger, greater than 1. As I told you, the Mach number of detonation, usual detonation, is the Mach number is typically, let's say, it's not more than 5, not less than 3. You see, it's between detonation between 3 and 5. You may have a little bit higher, 5.5, but not much. So it is supersonic, but it is of order unity. It's not large. There is no, and the burned gas is all the time UB relative to the gas is subsonic. Except at one critical point I will describe, which is the CG detonation. Chapman Jouet. Jump across a detonation. So I give here the reference of the John Lee book, which is for detonation is I do not agree with everything which is written in this book, but it is a good book for an overview of detonation. So now we are going to obtain the same jump condition, not the same, in a similar way as before, the jump condition across a detonation. Now, the detonation is here, is considered as a discontinuity, and I would like to know. Now I change notation, but it's not what is going to be the jump across this detonation. Now, when you do exactly the same thing as I did before, then when you consider now that you are releasing, that you have chemical energy, which is released by the reaction, you see, for a shock, you have only P plus 1 times nu plus 1 equal 1. But now, because of the energy which is released, you have this quantity Q, which is proportional to the heat release Qm per unit mass divided by a coefficient CPTU, because it's a non-dimensional thing. You know, Q is an energy per unit mass, QM. CPTU is an energy per unit mass. And so you have this ratio. And you have this Q here. Now, you see, the construction now is the same as before. You know, before, I have this Hugonot, the Hugonot of the leading shock. And now, because of the energy that you have, in addition, Q here, you shift what is called Hugonot after it release is different than Hugonot in blue inert. And this is simply shift by this quantity Q here. And now you have the same construction as before. You have the Rayleigh, the Michelson Rayleigh line here. Why I say Michelson? Because I will explain you that later. In fact, this is something that was not noticed until recently. That in fact there is a young student, a young Russian that did everything before Chapman-Jouguet. He did his PhD thesis and he derived the relation usually called Chapman-Jouguet relation much before him, not much, 3 years before, in his PhD thesis in Moscow. So sometimes good students. And it turns out when you have this, now you have the construction the same as before. You have the green curve and the red line that intersect in 2 points. And I will show you that this point, this one is not meaningful. I will explain you why. And this one is meaningful. This is a state behind the detonation, here, behind here, where this is gives you the pressure and the volume or the inverse of the density here on point P. And you see that if you were looking for the shock, you will be here. N, point N. This is the, and then because of the heat release, you are in B. This is the only difference. And what is very important is the following. And this was noticed first by Michelson, 1893. PhD thesis. He noticed the following, that by this construction, it is clear, you know, this slope decreases with the Mach number, propagation Mach number. Remember that it is the slope is minus because it is negative, the propagation Mach number. So when you decrease the Mach number, this slope decrease, and there is a marginal point below which you have no more solution, because you cannot cross the the green curve with a line starting from the unburned gas or ahead the detonation that has a slope smaller than this is critical slope. This means that you have a lower bound of the flame of the detonation propagation. And this lower band is called Chapman-Jouguet detonation. It should have been called Michelson, she was, but okay. Okay. What is important, I will just mention that before to go to the next slide, is that the main difference that you have, that the Mach number now here is a detonation. Now, okay, this is a detonation. All right. You are here, and if, how is my picture? Okay, on this picture, the detonation propagates from from right to left. So here I am sitting on the detonation front. Here I have D, and here I have UB. Okay, and here is the piston is somewhere behind, and this is going is propagate at the velocity of the piston. Okay, in the referential frame of the flame. So this is already a little bit tricky when you change laboratory frame. You know, from the laboratory frame to the frame attached to the detonation, this needs some exercise to see what the situation is. Okay, now d over the speed of sound here is larger than 1, mu, as a detonation. And this b, ub, but because the temperature is, here it is Tu, now here the temperature is Tb, burn gas temperature, and the sound speed is larger now, so you have ub divided by ab. This one is all the time smaller than unity, except at this critical regime, Chapman-Jouguet, where it becomes sonic. Okay? So this is all the time smaller, except at the marginal solution Cg, Chapman-Jouguet, okay, which is equal to 1. This is a picture that you have to keep in mind to understand. I don't know if all of you know that already, but I should see it. Okay. Here I have again written the same thing, same structure. Now this is the initial state here, and now you have this intersection with the Michelson-Rayleigh line in red, intersecting the Huguenot after it release. And in blue, you have the Huguenot before it release. So the picture is the following. Now, it turns out that to go from here to the green point B, you should go to the green, to the point N before. So you should go before to a shock, so you have a shock, what is called the lead shock of a detonation. Behind the lead shock, the temperature Tn has increased sufficiently to start the reaction rate, and the reaction rate is how do you say it, distribute in space because there is a flow velocity un, which pushes, and then you compensate the flow velocity with the heat release, and this is not a flame, as I discussed with one of the students. You know, this is not a flame. A flame is the balance of the heat release and the diffusion. Here, it is the balance between the heat release and the convection by the flow. From when you look to a referential frame attached to the lead shock. Okay? So this one is subsonic here. And it turns out, so this velocity here at the exit of the here, relative to the shock, this velocity is subsonic, except at the marginal state, there is no steady state detonation for propagating slower. There is no. And here it is sonic. Now, what it is easy to show is that now this reaction zone is macroscopic. It's not longer microscopic like a cross shock. It is macroscopic. It's easy to see that by balancing the heat release and the subsonic velocity. The difference is that now this velocity UN that you have relative to the shock here is much larger than the flame propagation, than the flame velocity. Okay, so the reaction rate is distributed because the flow is pushing back pushing back, and the temperature increase because of the reaction, and then you have this. This is now another important point is that you have another state here, which is predicted by such Roth analysis. And it turns out that this is non-physical. I am going to explain you. This is called sometimes a weak detonation. This has no meaning at all, as I am going to explain you. Except in one situation, maybe, that I will not have time to discuss. But this is non-meaning. I will explain you that. So now we have understood that what is called the Zeldovich-Neumann-Döring detonation structure. That is, a lead shock followed by a reaction zone which is convected because the temperature has increased, which is convected by that. Now, here are the order of magnitude to show you why this thickness is macroscopic. It's not microscopic. So you can use, this is very important, you can use the reactive fluid mechanic equation that you know to solve the detonation structure after the shock. Not the shock, but after the shock you can do. At the shock, you will use simply the Rankine-Hugoniot condition. Yes, this is explained here. I will skip this, why it is macroscopic. Now, what I am going, okay, nothing new. Diffusion rates, diffusion are negligible. Wait, yes, what is important to realize is that, let me be back here, is that now, as I told you, the structure of the detonation, this is called the inner structure of the detonation. It's a balance between the convection and the reaction rate, which is non-zero because the temperature is high because of the shock. Yeah? So a detonation is a shock-driven reaction wave. Okay? And what is easy to show is that here behind, the diffusion is negligible. Heat diffusion, which is a mechanism controlling the flame, is zero. It is negligible. And this, the order of magnitude, are shown here. So this is what you have to keep in mind, that the diffusion rate is negligible in the inner detonation structure compared to the reaction rate. So it cannot be a flame. That is the essential message. Now, in order to solve this structure, here you have the equation, mass conservation, momentum the same. The difference now is that you have the heat release here, and you have the progress variable here, and here is the equation of the progress variable. You see the equation of the progress variable is given by the convective effect and the reaction rate. If a very interesting result is obtained when you eliminate from these two equations P and rho. In order, when you do that, you end up with this relation linking the square of the flow velocity, its derivative, how it evolves, this square, with the progress variable of the reaction. This tells you how U square evolve with the progress variable. This is going, when you take this equation, you eliminate P and rho, and you find out a relation between U square, the derivative of U square in term divided by psi. Given here, you have only, what are the parameters? U, okay? And A square, but it is on the denominator. With this, when you have this, you will understand more easily what the situation is. This is called the phase portrait in the plane psi U square. This is the plane psi by psi U square, okay? Blue here is a Neumann state. Green here is the initial state, unburned state, okay? And this red point is here. This is a state behind the detonation when the heat is released, okay? So, when you are, because you are looking how to go from this point to this point, when you solve this equation here, you obtain this curve. Okay? Now, if you decrease the slope, the red slope, you end up with this curve, which is now when you go from here to here, okay? And that is a CJ wave, Chapman-Jouguet wave. That's very clear. And now, below, when the slope here of the Michelson line is smaller, there is no relation because you cannot have a trajectory leaking from the Neumann state. It turns out like that, and it never reaches the complete reaction. So that below this marginal state, there is no more solution, steady-state solution for the inner structure of the detonation. Now, it will be interesting to better understand why this point B, why this trajectory here is non-physical. In this trajectory, you are going from this point directly to the burn point without going through the lead shock. So you can ask, why is this? What is this solution? This solution is called, as I say you, a weak detonation. This is, to my opinion, is a very bad idea to call that detonation even weak. It is not a detonation, and it does not exist as a solution of the equation, except in a transient way for a very particular problem that I am not going to speak to tell you because it's not very important. Now, let me be back to the lecture 6 that I have skipped and the slide 6 of the lecture 6 because, okay, I escape, because I want to tell you something about the chemical reactions. So 6. Okay, here I am. In order to understand that the other point that I showed to you is not physical, you have to be back to the chemical chemistry. The chemical chemistry of a combustion is more complicated than the Arrhenius law in the one step, because you have many equations, many species, and so on. This is not all the time important, except in one point. The point is the following. You see, it's when you look to, for example, these are the main reactions for hydrogen-oxygen. It turns out that all this reaction that produce radical H is a chain branching reaction in such a way that oxygen, a molecule of oxygen and 2 molecules of hydrogen is producing a molecule of water, which is a product, plus a radical. And then the other reaction here that you have, this one are only important for initiation, but it's not what I am going to discuss. This is what is called a chain breaking. Now the radical recombine to produce again water. In order to schematize this complex chemical chemistry, you need only a simplified two-step model. First step, the R is a reactant. X is a radical. And this reaction produces 2X. You increase the number of X, you consume 1X, and you produce 2X. Okay? And this occurs with an Arrhenius law. Okay? Now, these radicals recombine with by another a third body to give a product which is a stable product, and heat release. I forgot the heat release for the first reaction, which is a chain branching, because it is not important to understand what I am going to explain. Now, in such a way that you see that the reaction rate of the branching reaction is proportional to the concentration of the reactant and concentration of the species and an Arrhenius law. Okay? So if I plot the Arrhenius, this rate of reaction in terms of the temperature for a given concentration, I have something like that. Strongly increase with the temperature. Okay? Now, if I what this reaction is almost not depending on the temperature. So the reaction rate of this reaction is just in blue. It's weakly depending on the temperature. So that it turns out that you have what the chemists call, or they say, the theoretical chemists call what is called a crossover temperature. When you are below the crossover temperature, you consume faster the radicals than you produce the radical. You see, you produce with this velocity here, and you consume with this velocity. Such a way that you cannot develop the concentration of radical. So there is no flame, no combustion possible below this crossover temperature. It is not quite true. There are other mechanisms called, people say that they call that low temperature reaction rate, but this low temperature mechanism are not involved in real flame. They are involved in what is called cool flame, which are very strange things that are nothing to see with a real flame. So for a real flame, the conclusion is the following. Below a crossover temperature, the reaction rate is 0. So you have a minimum of temperature to start. And this is very important because this crossover temperature typically is between, let's say, to be sure, let's say 800 K to 14, 1500 K. That's all. You're in between. So a reaction, combustion can proceed only for a temperature larger than that. Let's say the exothermal reaction the strongly exothermal reaction can proceed only at high temperature. So when you are working like I did with a single Arrhenius, with a single one-step reaction with an Arrhenius law, you just have to add that there is a crossover temperature. You just have to say, okay, this is a good relation, except below a crossover temperature where the reaction rate is 0. That's the only modification that you have to add to this simple model to well describe what is called the quenching, the chemical quenching mechanism. So now I can be back of my lecture, because this, I was supposed to give this before, but I prefer not to do that, because I want to keep time for the detonation. Now, back to lecture 10. Okay. Now, what is very simple to understand is that at that point here, in the fresh mixture, there is 0 reaction rate. And because the temperature here is below 300 K, and you need at least 800 K to start the reaction. So it is impossible to start the reaction from this point to have a wave propagating. So this kind of solutions that you obtain from that are not meaningful, because you should add the fact that there is a crossover temperature. When you add this, the only possibility is to start from this point, the Neumann point, where the temperature is above the crossover temperature. You know, when the shock is sufficiently strong to have a temperature in the behind the shock, still, you know, the shock is inert. Why it is inert? Because you have only few collision of molecule across a shock. Very few, very few. So this is elastic collision. But you have 0 non-elastic collision to produce heat. So shock is inert, but it increases the temperature. And now the reaction starts. But you need a shock. So a detonation is a wave controlled by a shock. It's a shock control wave, combustion wave. This is quite the opposite of a flame. A flame, there is no shock. It's controlled by the diffusion. Here, the diffusion, once again, the diffusive process are all completely negligible in this planar detonation, except in the shock itself, where it helps to increase the temperature. It is, you know, it is only inside the shock that you need the dissipative process, meaning you need the collision between molecules. Okay? So this is, and it turns out, you know, at the beginning of the century, people, you know, detonation was observed, in fact, in the 18th century on solid propellant in the Nobel laboratory by an engineer which was looking to how you call that? An explosive, line of explosive, ignite, because Nobel was building explosive, and the scientist, he did a fantastic job. He was able to measure front propagation up to 3,000 meters per second in a thing which is not larger than that. You see the resolution that you need for the time to measure something like that. He was very, very, at that time, because at that time there was no electronics. So he has, it's a fantastic job. And what he did, this is called a coton poudre in French. I don't know the name in English. He has this explosive, solid, line, ignite. Oh, you see something propagating. Okay, let's say something like 20, 30 centimeters per second, a flame. And at that moment, it starts differently by a charge or another explosive, and then you see something propagating at 3,000 meters per second. And this was reported in the Nature journal. This Nature journal, Scientific. They say, we never see something propagating as fast as what sees this man in his laboratory, except for light and electricity. So this is to tell you that beginning in the 18th century, they know that detonation exists, and now something was very strange for the physicists. How can a reaction can propagate faster than the sound? Why? Because the sound is a characteristic velocity of the molecule. A molecule is typically the sound. How can we go faster than the molecule? This was very, it was a question, and it is because there was a main difference between the scientists in fluid mechanics and the scientists in chemistry. Because a scientist in chemistry think about how to propagate this so fast. You need very, very light molecule, because the light molecule propagates faster than the mean one. Say, okay, it is because this radical is propagating so fast in front. That's completely wrong. Except one chemistry called Viel, this one. He said, okay, don't worry. There is this shock that has been described previously by Riemann and also observed by, I don't remember the name. They observed that. How they observe? You know how they observe shock? They put a gun, send, how do you say that? A ball, the gun, bullet. And they look to the stroboscopy of this, not stroboscopy, and they found out that there is a discontinuity in front of it. And this was the first time to see to see the shock. So at that time, you see, shock were something not very really understood. Chemistry was not really understood. It was a time where it was very interesting to work in science, because you are discovering very important phenomena. Now it is more difficult because so many scientists work before us that there is less things to discover easily. The things to discover now are more difficult than at that time. Okay, so Viel was was an intermediate to tell you that some chemists understand that what Zeldovich and this they'll think about that in around the 1920. And the first structure called Zeldovich-Neumann-Dering structure, that is the one driven by a shock, was developed, the theory, just around the 40s. So you see, some are understood. Okay. Good. This is for the story. So this branch is non-physical. Okay with Weyl conjecture. Now, let me try to understand a very important point. It is what is going to happen. This is, I recall you, the structure here. And the problem is, what happens when in my experiment the piston, shock, and a detonation here. This detonation was supported by the piston. We call piston support detonation. This is called an overdriven detonation. And all the detonations are overdriven except the Chapman-Jouguet detonation that are self-propagating. Why? They do not need the piston to push behind. Why? What happens when you have this overdriven detonation? That is when when the velocity of the piston is not zero. So yeah, and then what you do? Stop the piston. What happened? It is so. This is before to stop. You have the velocity. It is the velocity. You have the velocity behind. You have the Neumann velocity here, and this is propagating this structure here. Overdriven detonation is propagating support by the piston. Now you stop the piston. What is going to happen? Because you stop the piston, you are going to have a zero velocity on the piston. So you should link the zero velocity of the piston to the Neumann velocity that you have here. And how this is going? This is going to be realized by an expanding wave behind that decreases the velocity and also the pressure behind in the burn gases toward the zero. Okay. So yeah, this is a rarefaction wave that is developing behind. And as I am going to explain to you, the leading edge of the reaction wave is going to propagate relatively to the flow at the sound velocity. But because of the subsonic characteristic at the Neumann state, as I told you, UN is smaller than AN, this point is going to catch the exit of the detonation. Okay? And now what is going to happen? When it catch, now you have a sonic condition here. And this sonic condition you have protects the structure to any disturbance coming from behind. Because every disturbance cannot go faster than the sound speed. In fact, you know, it is like a screen. You screen? Oh, yeah. it is screened, the detonation structure Chapman-Jouguet is screened by any perturbation from behind. And it propagates, it is self-propagating. It does not need a piston behind to be sustained. So in fact, the detonations that you see in the lab are not piston supported, they are not overdriven. What you see usually is a Chapman-Jouguet detonation, which is the marginal solution of the problem of a steady-state problem of inner structure of detonation. Okay, here I have shown to you, but it's not necessary to spend time for you to understand that. What you see, this is overdriven detonation in black, and at that time 0 here, time here, you stop the piston. When you stop the piston, you see there is a fan here, characteristic curve, that propagates, that open, and the fan catch the exit of the reaction zone and then protect from further expansion that is developing behind, and you have the Chapman-Jouguet velocity, which is reached asymptotically in time. And it is a simple calculation show you how you reach the Chapman-Jouguet detonation. So this is what I want to see. Okay, now let me go to the next lecture, which is a very important and a difficult lecture. This one were easy. I don't know if you agree with that. Up to now, the lecture were easy. Now we are becoming to enter into real life, real problems, difficult problems. The real problem important are difficult to understand. No problem. You need an effort. You need an effort of thinking in order to understand the real important problem. And it is so difficult that I want to be sure to have my note not too far from my... Okay. So, the problem now is that I am going to address is how do you initiate a detonation? How can a detonation can be initiated? It's not easy to initiate a detonation. And this is a good thing, because if the detonation were easy to ignite, it will destroy everything. You know, a detonation will blow up the building, for example. You know, so okay. In fact, there are three types of mechanism to ignite a detonation. So you have a medium, and in this medium, you want to ignite a detonation. You have three types. I will not describe this type now. I will describe in my lecture, in my further lecture. Let's start with the first mechanism, which is called a direct initiation. What is a direct initiation? Okay, the first thing is that if you want that to have a detonation, the first point is that the mixture should be detonable. That can support the detonation. It is not so clear. To support the detonation, the Neumann temperature, because you say there is a shock, should be larger than the crossover temperature. So, first of all, you need that. You need a mixture such that the Neumann temperature of the Chapman-Jouguet is larger than the crossover temperature. Otherwise, you will not have a detonation. This is the first point which is written here. So this is what I call a detonable mixture. So we are talking about how to ignite a detonation in a detonable mixture. I have recalled here the basics I have just presented in my previous lecture. Some basics are recalled in this. Well, this is the what's that? Flow of burn gas behind you as a discontinuous. Oh yeah. In order to understand the way to initiate, we have first to understand how the flow of burn gas behind the CG detonation. What the solution for that? View as a when the detonation is viewed as a discontinuity, you want to know what is the flow behind. So we are going to start in a spherical geometry of we are going to think about a spherical detonation propagating outwards, okay? And you want to know what is going to be the flow field behind in the burn gas. So you have, okay? So you have, this is my detonation, propagating, and I want to know what is the flow field behind. It should be a CG detonation because there is no piston supporting the detonation. So this was developed by Zeldovich and Taylor in the middle of the last century. And the reason for that was associated with the development with atomic bombs, in fact. This is why Zeldovich and Taylor, for example, Taylor developed that in the 38, I think, or no, in the 40s, a little bit before Zeldovich, but it was kept secret, you know, because it was related to the atomic bombs. And when Zeldovich succeeded to publish this work, because he also surely did the work a little bit before, and it was kept secret. Taylor decided to publish his report. These two men were developing, so what I am going to explain to you, the rarefaction wave behind the planar CG spherical detonation. No. Okay, so before to study the spherical, I am going to study first the planar, and then we will see the difference with spherical. So what you are looking to, the solution you are looking for is what is called, these are particular solution called self-similar solution. What does that mean? Does that mean that the position and the time appear, you know, the problem is one-dimensional. Here it is planar, but here it is planar, but it is, so you have R, X, and T. And it turns out we are looking for solutions such that R and T appear only through the ratio R over T. This is called a self-similar solution. So when you change a variable, in that case, you change a variable. This is how you change R in terms of X, which is the self-similar variable. This is the time, because for the time you have to divide by X if the solution depends on, and then divide with respect to time, and this is going to give you R divided by T squared. And this is simply X d over dx over T minus. So when you change this variable, this is a mass conservation equation that you have. You see, you have only one variable now. Why it is a very important, why this self-similar assumptions simplifies drastically the problem, is that you have only one variable now, because time and space as related by the ratio is constant. So you have this kind of variable. You can eliminate now the density. This is the pressure, you know, when you assume isentropic relation. This is the pressure. This is a continuity equation. This is a momentum equation. And you eliminate here the density, d rho over dt. What do you obtain? An equation like that, dv over dx time a factor which is 1 minus the square of the ratio velocity, velocity, which is here, minus x here, divided by a square equals 0. If you assume that you have a solution, that means that dv over dx is not 0, this implies that you should have this relation, that the velocity should be x minus a, the reduced velocity. And you have this Riemann invariance that I have written here, and I skip the detail because I will have too much time. And it turns out that here you see this. This is the leading edge of the rarefaction wave, okay? Starting behind a detonation, behind a shock or a detonation. And this is in the vertical axis, you have reduced V by the DCG, the Chapman-Jouguet detonations time coefficients that gamma plus 1, it's not important. Because you know that the velocity here should be unity behind the detonation. Because I am looking to a Chapman-Jouguet detonation. So I know what is the flow behind the shock. So, and here on the horizontal axis, I have, in order, it is not R over 2, it is R over 2 divide to have a non-dimensional number divided by the detonation, Chapman-Jouguet detonation, which is well done, which is well defined. And it turns out that the solution is the following. That all the details are here. That rarefaction wave in this diagram, where the leading edge is propagating at the Chapman-Jouguet velocity with a 0 velocity in the center. At one point, we are looking to a planar, this close, and you have Chapman-Jouguet detonation propagating here. And what is developing here, you look what is the structure that you have here, and this is simply the velocity is in this diagram, where in the horizontal axis you put r divided by t, not r. This is simply a straight line. So this is easy to. The solution is come immediately from that. What is very important is that you have a core of burned gas at rest. Okay. You know, you have a core. This is burned gas at rest. The velocity are decreasing here, go to 0 here, and here the velocity is 0. So you have what is important is that, and this core here, this is burn gas, a core of burned gas at rest. And the leading edge of this core is propagating. This is increasing with time. Increased propagation with the time. But the leading edge of this core propagates with the sound speed in this core at rest. This is called a weak discontinuity. It's not, this is like now, this was and here are the solution. You see, this here, you have the solution V in terms of X. X is X. Here I have X divided by dCg because X is a velocity. And so you have, here is the velocity, the solution that you have here. Okay? This is a simple exercise. Now, a most difficult exercise, which was obtained by Zeldovich and Taylor, this was the case of a spherical detonation. Now, spherical propagation, what is the situation? And why this was very important for the weapons, for the nuclear, because now you are going to obtain the structure of the flow inside, and it is the problem I am going to describe is not related to an explosion, but the problem is quite similar. So if you know how to solve this problem, you will know by simply looking at the velocity far away from when you have an explosion, when far away, you look to the velocity of the shock. If you know the history of this velocity by a camera, for example, you will know what is the energy that has been developed by the bomb. And this is why this was people cannot, they did not publish this work because it is very related to the other. So now, what's the problem? The problem is exactly the same as in the planar, except that in spherical geometry, the Laplacian involves the radius. You know, in the planar geometry, here, no, not the Laplacian. I say something wrong. The divergence. The divergence of, the divergence, this is, in planar, the divergence is simply the derivative of the velocity divided relative to the radius. In spherical, you have the change is that the divergence in geometry, in spherical geometry, involves the radius here and here. This is the only difference. So now the only difference when you are looking to the self-similar solution is to have an additional term here. Now it is here are the results. It looks like now it is not a straight line here. You see, this is the pressure, the density, the temperature, and still in terms of the radius variable on the vertical axis and on the horizontal axis is a self-similar space variable. Now, so it turns out that this problem, I will skip the detail because it's you can do if you're interested. It's not difficult to do, but there is an important point, main difference with the planar, is that you can show that now this slope here, you know, is infinite. You see, okay, Here, the slope is finite, is the same everywhere. It turns out that in spherical geometry, because of this term, additional term, the slope becomes infinite. And this was terribly boring. Because if the slope is infinite, how you can consider the detonations as having a zero thickness? Because you do not have any length. You know, the characteristic length that you have is the radius. Unfortunately, the slope is infinite. The length disappears. So you have no more length. So the length, in a sense, the length becomes, the characteristic length goes to zero. So you can no longer treat the detonation as a discontinuity. This was written explicitly in the to begin in the paper of Taylor. He said, yes, okay, we find something interesting, but there are something difficult. This needs further analysis because this solution has a difficulty, which is this one. Okay, you have all the calculation to show how this CG condition, this is associated with the CG condition. Okay, let's have 50-minute breaks.